Так, кажется, что все окей. Тут и там, да? Я надеюсь. Так, давайте мы проверим. Let's check that everything is fine online and offline simultaneously. Yeah? Ну, тот, кто офлайн, явно меня видит, да? Нормально, меня видно. Да, хорошо. And that, so what about online?
Yeah, we can see.
Students?
Yeah, we can see.
Okay. Then we can start. Okay. Today we will discuss the solution structure of ARMA type equations. So we will discuss the number of solutions and the type. Are they stationary? Are they non-stationary? If we start with autoregressive moving average type equation. Okay.
I have a question.
Yeah.
Today's lecture will be like guided by you.
Yeah.
I see that. I just we haven't got this. Maybe I was the warning, so I was just confused. Maybe it's like the same time two things.
No. Okay. So first, let's write. So A of L will be some lag polynomial, of degree A of L will be equal to P. So A of L is something like I don't know, 1 plus 2L plus 3L squared, something like this, lag polynomial of degree P with initial coefficient normalized to 1. So initial coefficient will be 1. That means A of 0 is 1. Yeah? A of 0 means the initial coefficient is 1. Yeah? M of L will be another lag polynomial with probably different degree of this M of L polynomial will be Q, and the same normalizing condition applies. So M of 0 will be 1. So once again, example is something M of L is equal to 1 minus 0.3 L plus 0.07 L squared. So they are lag polynomials. A of L and M of L are two lag polynomials with a normalizing condition. This normalizing condition we assume that the first coefficient, the coefficient without L, is normalized to 1. That's okay? Yeah. So we have two polynomials. Let's consider ARMA, let's say ARMA type equation. That's not yet a process. I will state once again that that is equation. A of L multiplied by YT minus mu is equal to M of L multiplied by UT, where UT is a white noise. And as you see, obviously, that's an equation. Yeah, you have left-hand side, you have right-hand side. If you have left-hand side, if you have right-hand side, then that is an equation. Yeah, okay. Just let me recall what a white noise is for members. What are the assumptions for white noise? Yeah, expectation of UT is 0. What else? Constant variance. Variance of UT is equal to gamma 0. Yes, for white noise, you are exactly right. Covariance of UT and some US is equal to 0, provided that T is different from S. Because if T is equal to S, we will just get the variance. Yeah. Okay, and so this is an equation, and we try to solve it for YT. So from this equation, we'd like to obtain the process YT, and we wonder how many solutions do we have, how many stationary solutions do we have, how many, so what are our questions? So we will discuss today the following questions. First question is very easy. How many solutions do we have? How many solutions do we have? Point B, how many stationary solutions do we have? How many stationary solutions do we have? And the point 3, how many solutions of the form YT is equal to some constant mu plus MA infinity process with respect. That's okay if I write WRT for with respect to, yeah, that's okay, with respect to UT, how many solutions of the form YT is equal to mu plus moving average with respect to UT do we have? Or I may be explicit, YT is equal to mu plus UT plus some coefficient before UT minus 1 plus some coefficient before UT minus 2 plus blah, 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 UT minus 3. I think just a moment, I hope. I think that's okay. So let's start. First question is very easy. Just consider 2 examples. So to answer the first question, we just need to consider 2 examples. If you have an equation like this, YT is equal to I don't know, YT is equal to 5 plus UT plus 0. Let's consider the following 2 examples. Example 1, example 2. YT is equal to 5 plus UT plus 0.7 UT minus 1 plus 0.2 UT minus 2. And YT minus 0.3 YT minus 1 is equal to 5 plus UT plus 0.7 UT minus 1 plus 0.2 UT minus 2. How many solutions does the first equation have? How many solutions does the second equation have? How many solutions? If we don't care about the stationarity, about the properties, how many solutions, how many YT can you find?
In the first, it should be 1.
Yeah, we have unique solution because YT is written, yeah? You have no choice. YT should be equal to 5 plus UT plus 0.7 UT minus 1, yeah? So you have no choice, you have no freedom in the first case. So the number of solutions, well, the number of solutions, we have unique solution for the first equation, And the second equation, how many solutions do we have?
Infinitely many?
Yeah, infinitely many, because we have a degree of freedom. We can choose, let's say, y0. Yeah, we can choose any y0. Yeah, why we have infinitely many solutions here? Yeah, you can write y0 as we wish. As we wish. Yeah, we can write here y0 u7 divided by u0 plus, I don't know, 7. And then we can calculate y1, y2, y3, using the recurrence relation. Okay, yeah. So we can choose any y0, and as we can choose any y0, so we can obtain infinitely many processes. Okay, so the first theorem is obvious. Theorem 1, that's very easy. If degree of A of L is bigger than 1, then the equation A of L times yt minus mu is equal to m of L times ut has infinitely many solutions. Yeah. So if we have at least one leg in the polynomial A of L, then the number of solutions is infinite. And if if A of L is just equal to 1, so there are no leg in the first polynomial, then the equation has a unique solution. And I think the proof is obvious, yeah, because if you have no leg in the equation, oh, just yt is written, you have no freedom. Yt is given. And if you have at least one leg, then you have freedom. You can choose y0. And if there are two legs, then you can choose y0 and y1 and deduce y2 from the equation. Okay, now the first theorem is more or less obvious, just obvious from examples. And the next theorem is much harder. We will not prove it because it requires a good knowledge of complex analysis. Okay. Is it okay? So just a small definition. We say that A of L and M of L are coprime if they have no common roots. That's okay? Do you understand what are coprime polynomials? Взаимно простые in Russian, so they have no common roots. Just an example, let's say 5 minus L and
yeah, we understand, like, what does it mean? That they are just no similar roots, right? It's just
roots are different, yeah. So for example, 5 minus L and 25 plus L squared minus 10L are not coprime. Not coprime, yeah, because that's basically 5 minus L squared, yeah. And for example, 1 plus 0.3L and 1 plus 0.7L are coprime. They have no common roots. Okay, so let's now, if we understand what are coprime polynomials, then we can state the next theorem about the number of stationary solutions. Once again, we will not prove it. Theorem 2 about the number of. So the theorem 1 is obvious from 2 examples, but the theorem 2 is hard. Good knowledge. Complex analysis required. Complex analysis for the proof. It says if A of L and M of L are coprime, if A of L and M of L are coprime, then equation A of L times yt minus mu equal to M of L times yt, where ut is a white noise, has unique stationary solution if and only if A of L has no unit root. If A of L has a unit root, then there are no stationary solutions. There are no stationary solutions. What is a unit root? What is a unit root? Maybe it's better to say, oh, no unit root has no roots L with absolute value equal to 1. Yeah, has a root L with absolute value equal to 1. Yeah, that's better to say has no roots L with absolute value equal to 1. Okay, let's provide some examples. Once again, we will not go into the proof of this theorem. It's hard. Just we will believe it and consider some examples and we will use it. Okay. So let's consider the following example. Example 1. 1 minus yt minus yt minus 1 equals to ut plus 7. Oh, okay, equals to ut. Plus 0.3 ut minus 1. And the question, how many stationary solutions do we have? Okay, let's write it using polynomials. So if I write the same equation using polynomials, it will be 1 minus L times yt equals to what? Okay, I see that these two polynomials are coprime. Yeah, so the theorem is applicable. Yeah, these two polynomials, 1 minus L and 1 plus 0.3 L are coprime. The theorem is applicable. If I consider the roots of these of the left, so this is A of L, this is M of L, they are coprime. So the theorem is applicable. Obviously, if I will solve A of L equal to 0, if I will find the roots of the left hand side polynomial. 1 minus L equals to 0, L equals to 1, absolute value of L is obviously equal to 1. Yeah, that's okay? Yeah. So according to this theorem, how many stationary solutions do we have in this case? No stationary solution. We have infinitely many solutions, but no stationary solutions. Okay. So conclusion, no stationary solution. Okay, example 2. Let's say we have something like yt plus yt minus 2 equals to ut. The same question, how many stationary solutions do we have? So let's write in lag polynomial form. 1 plus L squared times yt is equal to 1 times ut. This is my A of L. This is my M of L. Once again, they are coprime. Yeah. Okay, now let's solve A of L equals to 0. 1 plus L squared equals to 0. L squared equals to minus 1. What are the complex roots of this equation? Yeah, plus or minus I. We have L1 that is plus I, L2 that is minus I. Okay, what are the absolute values of these guys? What is the absolute value of L2 and the absolute value of L1?
It's 1.
1. Yeah, the absolute value is just the length of a complex. So you have two complex roots. Yeah, we have a real part. We have imaginary part. So we have plus I is here. Yeah, that is plus I. Minus I is looking downward. But basically, the absolute value of a complex number is just the length of a vector. Yeah. So the vector, these vectors, they have unit length. So according to this theorem, how many stationary solutions do we have? No stationary solutions. Okay, let's consider one more example. Example 3. Yt minus 1 equal to ut minus minus 1. The same question, how many stationary solutions do we have? Okay, once again, I write in a lag polynomial form. 1 minus L times yt equals to 1 minus L times ut. I see that this is A of L, that is M of L, and obviously they are not coprime. They have the same root. Yeah, not coprime. Not coprime. The theorem is not applicable. Yeah, the theorem is not applicable. Obviously, we have only one unit root, the root equal to 1. Yeah, if I solve A of L equal to 0, 1 minus L equal to 0, L is equal to 1. We have a unit root. Yeah, but the theorem is not applicable because the theorem refers only to the case when there are the polynomials are coprime. Yeah. Okay. And obviously, this equation, yeah, this equation has infinitely many solutions. Yeah, has infinitely many solutions from the solutions, And let's guess a stationary solution. Who can guess a stationary solution for this equation? Who can guess? Oh, that's not difficult. Who can guess a stationary?
Y0 equals 0.
No, that will be non-stationary, I think. So my advice, guess a stationary solution. Okay, let's see this equation. The elephant t minus elephant t minus 1 is equal to hedgehog t minus hedgehog t minus 1. Yeah, that has the form. Who can guess a solution? Yeah, so the solution, we can guess a solution. Yeah. So for example, if I take the solution yt is equal to ut, that's a solution. Yeah. That's a honest solution to this equation. Yeah. If you that's a guess. Yeah. But if you plug in this solution to this equation, obviously everything is satisfied. Yeah. That's a solution to equation 3. Yeah, to equation 3. And that's a stationary solution. Stationary solution. You can find even more stationary solution. For example, yt equals to ut plus 1. So if you plug in this, so that's also a stationary solution. A stationary solution to equation 3. Yeah. You can just check that that's a honest solution. Yt plus 1 minus yt minus 1 plus 1 is equal to yt minus 1. Yeah, that's okay. Yeah, that's the solution. Okay, but we also have so we have infinitely many stationary solutions in this case. Stationary solutions, because the theorem is not applicable. So the theorem says that either we have one unique stationary solution, either we have no stationary solutions at all, but then it's applicable when polynomials are coprime. When they are not coprime, different things can happen. And we have infinitely many non-stationary solutions. Non-stationary solutions for this equation. For example, if you take as advised y0 equal to 0, y0 equal to 0, then according to this equation, yt is y t minus 1 plus ut minus 1. Y1 will be equal to u1 minus u0. u2 will be equal to y1 minus u0 plus u2 minus u1 will be u2 minus u0. y3 will be equal to u3 minus u0, and so on. And this solution is non-stationary. Why this solution is non-stationary? If I start with 0, why this solution is non-stationary? You can tell me. If I calculate variance of y0, it is 0, because y0 is a constant. If I calculate variance of, let's say, y2, it will be variance of u2 minus u0. It will be
0.
2 sigma squared u. Yeah?
Oh, yeah.
It's added. Yeah, it's not when you have the variance of difference, it is sum of the variance. Yeah, you have sigma squared of u plus. Yeah, the variance is always non-negative, and that's non-stationary solution. And if you start with not with 0, but let's say with 5, or let's say with 10, we will obtain also a non-stationary solution. Okay, and the last theorem, we will not prove it either. Theorem 3. Theorem 3. As we have a little bit discussed, in many economics financial applications, so let's say first motivation. In many financial economics application, UT is considered, so from mathematical viewpoint, UT is a random variable. It has no sense from mathematical viewpoint. It's just a random variable, UT. But in many financial economics application, we consider UT is considered as a random shock that happens at time t and is independent of past events. So that's something new that happens at time t. Some news that were unpredictable before, something bad or something good that is unpredictable, is independent of past events. So if we'd like to use this interpretation, so from mathematical viewpoint, that's just an equation. That's just an equation. We are searching for a sequence of random variables. They have no real sense, and so any sequence of random variables that satisfies this equation is called a solution to this equation. But if we try to make sense of a sequence of random variables, we'd like to say, oh, UT is something that is a shock that happens at time t and it's unpredictable beforehand. Okay, in this case, the solution, so if I use this motivation, the solution of the solution like yt is equal to, let's say, 5 plus 0.3 ut plus 1 is something strange. Yeah, that's strange from this interpretational viewpoint. Yeah, from mathematical viewpoint, oh, that's a perfectly defined process. Yeah, we have no problem from mathematical viewpoint. Yt is equal to 5 plus 0.3 ut plus 1. From mathematical viewpoint, that's perfectly fine. Yeah, but from interpretational viewpoint, that says, oh, now we know something. So the weather now depends on something that will happen only tomorrow. Yeah, from mathematical viewpoint, that's perfectly okay. Yeah, from this interpretational motivational viewpoint, that's something strange. Okay. Yeah, and so that's why in many cases we search not we are searching not for stationary solutions, but for the next theorem. So that's a motivation for the next theorem. So if A of L and M of L are coprime, then no, I need one before the theorem and the motivation. I just need one more definition. Because there are two polynomials associated with the same equation. So let's consider 1 plus yt plus yt plus 0.3, no, let's say 0.5 yt minus 1 equals to, let's say, ut plus 3 ut minus 1. And we have two polynomials linked to each side, to left-hand side, to right-hand side. We have lag polynomial. Yeah, we have lag polynomial. We have lag polynomial. Let's consider left-hand side. Let's consider left-hand side. In left-hand side, we have a let's focus on the left-hand side, because for the right-hand side we have the same thing. So let's focus. Let's focus on the left-hand side. Okay, if I consider the left-hand side, I have lag polynomial a of L that is 1 plus 0.5 L. Yeah. Okay. That's fine. So I can write the left-hand side as a of L times yt equals to blah, blah, blah. So we focus on the left-hand side only. And we have a characteristic polynomial. Characteristic polynomial. What is a characteristic polynomial? Assume for the moment the simple right-hand side equal to, let's say, 0. Yeah. Assume for the moment no right-hand side. No right-hand side. So let's for the moment assume that right-hand side is equal to 0. And we have hence the equation of type yt plus 0.5 yt minus 1 equal to 0. So assume that right-hand side is 0 for the moment. And assume that we are searching for deterministic processes, not stochastic. Assume no right-hand side, and let's find deterministic solutions. As we have no source of randomness, we have replaced ut, the source of randomness, by 0, and let's find a deterministic solution. Probably, if you have studied in middle school, probably you know that that is an equation of geometric sequence. Yeah, yeah. Yt is something multiplied by the previous value. Yeah. You see? Yeah. That's just the definition of geometric progression. Yeah. Hence, we can search. Let's search for the geometric progression. Geometric progression. So let's say we search yt equals to lambda power t. So that's, I have omitted the initial, so the starting coefficient of this geometric progression is 1. Yeah. Y0 is 1 here. Okay, and hence I can write my equation like lambda power t plus 0.5 times lambda power t minus 1 equals to 0. If I cancel out lambda power t minus 1, I will get lambda plus 0.5 equals to 0. Yeah. Okay. And that part, lambda plus 0.5, that's called a characteristic polynomial, char. So let's say, how to call it, char a of lambda. Yeah, let's call it char characteristic polynomial. So that's lambda plus 0.5. That's very similar to lag polynomial, but with the order inversed. Yeah. So if I consider the lag polynomial a of L, it is 1 plus 0.5 L, and the characteristic polynomial is very similar, but the power increases in the opposite direction. Yeah. So let's consider one more example for the difference between lag polynomial and characteristic polynomial. That's a lag polynomial. and that's a characteristic polynomial. So let's provide one more example. Consider, we focus once again on left-hand side. Let's focus on left-hand side. For example, in left-hand side, we have yt minus 0.2, yt minus 1 plus 0, I don't know, 50, let's say 15, yt minus 2 equals to something, I don't care. So we focus on the left-hand side. So who can write me the leg polynomial, and who can write me the characteristic polynomial? Sorry, of lambda. Yeah, the first one.
So the leg polynomial is 1 minus 0.2 L plus 0.15 L squared.
Yeah, and
I guess the characteristic is lambda minus 0.2. Yeah, lambda squared minus 0.2 lambda plus 0.15.
Yeah, yeah. If let's obtain once more characteristic polynomial. If I replace yt by lambda power t, if I search the deterministic solution, the geometric sequence, so that will be lambda power t minus 0, 2, lambda power t minus 1 plus 0, 15, lambda power t minus 2 equals to 0. I can cancel out lambda power t minus 2, and then I get lambda squared minus 0, 2, lambda plus 0, 15. That's the characteristic polynomial. Okay, so we have a simple, maybe I should wait 1 or 2 minutes here. Everything is fine? Yeah. Two polynomials are associated with left-hand side, and the same for the right-hand side. You have leg polynomial of the right-hand side, you have a characteristic polynomial of the right-hand side. That's okay? Okay. We have a simple theorem. So you maybe we will leave it as a home assignment. I hope that you have enough. So if z is a root of a of L, then 1 over z is a root of z is a root of a of L if and only if 1 over z is a root of characteristic polynomial of lambda. So the root are inverse. Yeah, if you have 2, so for example, if you have an equation 1 plus 0.5 L, here is the root. If you will calculate the root, you will have minus 2. Yeah, but if you write characteristic polynomial lambda plus 0.5, if you will try to find a solution, yeah, you will get lambda is equal to minus 1 over 2. Yeah, the root are inverse. Okay. Yeah. So that's a leg polynomial. That's a characteristic polynomial. And now the third theorem, theorem 3. If A of L and M of L are coprime, then equation A of L times yt minus mu equals to M of L times ut, where ut is a white noise. If A of L and M of L are coprime, then the equation has a unique solution of the form yt equals to mu plus ut plus something times ut minus 1. You can write any letters there, plus something times ut minus 2. Oh, I may write alpha 1, alpha 2, alpha 3. Yeah, has a unique solution. So that's not forward-looking. Yeah, there are no future ut plus 1, no future ut plus 2, no future ut plus 3 in yt. Yeah. If a of L and M of L are coprime, then the equation has a unique solution of the form if and only if all roots lambda of characteristic polynomial of A of lambda are less than 1 by absolute value. So if at least 1 lambda has absolute value bigger or equal to 1, then there are no solutions of this form. Yeah, that's moving average with respect to UT. Okay, so let's consider some examples. Yeah, should I wait a little bit?
No, it's fine.
Okay, let's provide some examples. Once again, we will not go into the proof. That's hard, but we will look at some examples. Example 1. Let's consider yt is equal to 5 times yt minus 1 plus ut. Ut is a white noise. My question is A, how many stationary? So let's apply to maybe, yeah, let's answer all 3 questions. Now we have 3 theorems. We can answer all 3 questions. Question A, how many solutions? How many solutions? Question B, how many stationary solutions? Question C, how many solutions of the form yt is equal to mu plus ut plus alpha 1 ut minus 1 plus alpha 2 ut minus 2 plus so on. Okay, who can answer?
I guess there are infinitely many solutions.
Infinitely many. Yeah, you can choose any y0. And if you choose y0, you can deduce y1, you can deduce y2, you can deduce y minus 1. Okay. How many stationary solutions do we have?
One?
Yes, we have 1 stationary solution. Because if I write 1 minus 5L times yt is equal to ut, so A of L is 1 minus 5L. Yeah, and if you try to solve it, you will get L 1 over 5. Absolute value of L is not equal to 1. So we have 1 stationary solution. But that stationary solution is not motivated by economics or finance. So the answer to the point C, how many stationary solutions do we have? Sorry, how many solutions of the MA form do we have? The questions 0. Yeah, why 0? Because if we calculate characteristic polynomial of the left-hand side, what is the characteristic polynomial of the left-hand side?
Lambda minus 5.
Yeah, that's lambda minus 5. Yeah, that's the so they are very similar, but the power of the unknown increases in the other direction. Yeah, it's 1 minus 5 but it's lambda 1 lambda minus 5. Okay, so if I try to solve it, lambda is equal to 5, obviously, and the absolute value of lambda is bigger than 1. Yeah, bigger or equal to 1. Then 0 solutions. 0 solutions of MA. So 0 solutions of the required form. Okay? And that's the general case. Yeah, that's the general case. So if we look at the structure, these are solutions. These are stationary solutions. And these are these are solutions of the form. We consider the equation A of L times YT minus mu is equal to M of L times UT. We consider this equation, and that's a general case. We have the set of all solutions, the set of stationary solutions, and solutions of the form YT equals to mu plus UT plus alpha 1, UT minus 1 plus alpha 2, UT minus 2 plus so on. So the biggest set is a set of all solutions. The set of stationary solutions is a subset of the set of all solutions. And solutions of this form is a subset of stationary solutions. Okay? Yeah. And in many cases, so if you will, so that's a standard slang, and implicitly, in many cases, in many good books, in many good sources, the authors say, oh, how many stationary solutions do we have? And they are really searching for stationary solutions of this form. So that's the standard implicit agreement. Yeah, so that's probably, I'd like to point this out, that there is a difference between stationary solution and the solution of the MA form, but in many cases you will just encounter in many books that, so for example, if you look, I don't like to waste time, but if you look, for example, at the econometrics Olympiad organized by Moscow State University, and you will look through the questions, and they usually write the equation of MA4 of the process, and they ask students to find stationary solutions, but they really mean stationary solutions of the that are not forward-looking, that do not look into the future. So that's a standard implicit. So in many, so let's write it, that many authors implicitly assume that YT has a form that YT does not does not depend on future ut plus 1, ut plus 2, and so on. So they implicitly assume this form. Okay, let's consider some more examples. And that creates a problem for a student because from mathematical viewpoint, that's a big difference. So you have solutions, you have stationary solutions, and you have a subset of stationary solutions of specific form interested into economists and other professionals. Okay, so probably let's consider more examples. YT minus minus 0 to minus 0, 3 YT minus 1 just a moment. Okay. Oh, I need no, let's say plus 0, 3 plus 0, 28 YT minus 2 is equal to T plus 7 UT minus 1. Once again, how many A, B, C? The same questions. How many solutions? Just one more example. How many stationary solutions? How many solutions of the form YT equals to mu plus alpha 1 UT alpha 2 UT minus 2 plus so on. So the same question. Once again, UT is a white noise. Please break them up. Okay, A is very easy. We have infinitely many solutions. Why? Yeah, you can choose any y0. You can choose any y1. You have even more degrees of freedom here. Yeah, you can just write y0 is 7. You can write y1 is I don't know u2, and you can deduce y2, y3, y4 from the recurrence relation. Yeah, that's okay. You have even more degrees of freedom in this case. Yeah, you choose any y0, any y1, and the recurrence relation will give you y2, y3, y4. Okay, B. So let's write A of L. A of L is 1 plus 0, 3L plus 0, 28 L squared. What is M of L? 1 plus 7L. Let's write the characteristic brothers. Yeah. So we have a characteristic brother of A of L. And what is the characteristic brother of this polynomial? Yeah, lambda squared plus 0, 3 lambda plus 0, 28. What is a characteristic brother of this M? Lambda plus 7. Okay. So let's check. Do they have common roots? Or do they have common roots? You can check the common roots of characteristic polynomials, so you can check the common roots of flat polynomial. Yeah. So they are. So A and M will be coprime if and only if characteristic A, characteristic M will be co-prime. Yeah, you can check that. Okay, let's find the roots of characteristic polynomials. Okay, lambda plus 7 equals to 0, lambda is equal to minus 7, okay? And lambda squared plus 0.3, lambda plus 0.28 equals to 0. Okay, what are the roots here? What are the roots? Lambda 1 plus lambda 2 is 0.3. Lambda 1 multiplied by lambda 2 is 0.28. Yeah. What are the roots? I've confused. Okay. So, okay, let's find the roots. Okay, the discriminant is 0.09 minus 4 times 0.28. That's less than 0. So that's 0.09 minus 1.12. Yeah, 12. That's minus 1.03. Lambda 1 second is minus 0.3 plus plus or minus I square 103 divided by 2. Yeah, we have complex root, but that's not a problem. Okay, I see that the polynomials are co-prime. Yeah, no common root. Yeah, that's okay. Okay, now we need to calculate the absolute value of lambdas. What is the absolute value of lambda 1? Let's say the absolute value. How to calculate the absolute value? If you have a complex number z equal to a plus bi, what is the absolute value of z? Yeah, that's the square root of a squared plus b squared. Yeah. So once again, you just calculate the length. We have a real part on a horizontal axis, imaginary part on the vertical axis. That is something like a plus bi, and we just use Pythagorean theorem to calculate the length. So once again, this is just the length of a vector, yeah, of z, and the length is positive or 0. The length is not imaginary. Okay, so we have square root of minus 0.3 over 2 squared plus square root of 103 over 2 squared. Is it bigger than 1? Is it less than 1? Yeah, it's less than 1. Yeah, okay. That's okay. So that's less than 1. If you calculate the absolute value of the second lambda, nothing changes because you will get minus inside brackets. Yeah, be careful. Get minus inside brackets. So all roots of characteristic polynomial are less than 1. Hence, what are the answers? So we will simultaneously answer B and C. What are the answer for B? What are the answer for C? Yeah, for B unique and for C. Yeah, that's the same solution. Yeah. So we have infinitely many solutions, one stationary solution, and this stationary solution has special form that does not look into the future. Yeah. Okay, that's a little bit hard to write it explicitly. Yeah, that's a little bit hard to write it explicitly, but we can if we wish. Okay, that's fine. Okay, let's consider one more example. How many? I have 3. Okay, I think we will finish a little bit earlier because of the battery. Sorry, but okay. Anyway, Saturday we can finish earlier a little bit. Okay, yt minus 1. No. Minus 2 yt minus 1 plus yt minus 2 is equal to ut plus 0.5 ut minus 1. The same question, how many A, B, C? I'm a little bit lazy to copy questions. How many solutions? How many stationary solutions? How many yt equals to mu plus ut plus alpha 1, ut minus 1 plus alpha 2, ut minus 2 plus solutions. Okay, let's write lag polynomials, characteristic polynomials, and let's probably the A. Who can answer the question A? Yeah, infinitely many. So the first question is very easy. Okay, let's write the lag polynomial A of L, M of L. Let's write characteristic polynomials. And characteristic? Yeah. Okay, so let's solve all these equations. Characteristic. I will solve characteristic equation, but you can solve the lag equation. Lambda plus 0.5 equals to 0. Lambda is minus 0.5. Lambda squared minus 2 lambdas plus 1 equals to 0. Lambda 1 is 1. Lambda 2 is 1. Okay, what is the conclusion? Yeah, no stationary solutions and no MA form solutions. Там села у планшета батарейка, поэтому мы все прекрасно закончили, в общем, с примером.
Хорошо, спасибо. До свидания.
Ага, хорошей субботы, хорошего.
Вам также всего хорошего.
Вам тоже хорошей субботы.